Greetings viewers, welcome to our channel which is Radioactivity. As for today we are going to concentrate on radioactivity. So when dealing with radioactivity, the first thing you have to know is the definition of radioactivity. So the definition of radioactivity, this is the spontaneous disintegration of unstable nuclei emitting alpha and beta particles and gamma ray. So we are going to write the definition of radioactivity as this is the spontaneous disintegration of unstable nuclei emitting alpha and beta particles and gamma ray. So after knowing the definition of radioactivity, we also have to know the definition of a radioactive element. So a radioactive element, a radioactive element radioactive element. So a radioactive element, this is an element, or this is an unstable element that undergo radioactivity, that undergo radioactivity. Now, after knowing the definition of radioactivity and a radioactive element, there are also some characteristics of emissions of which we need to discuss, and these mostly comes under multiple choice questions. So we are going to move on to discuss the characteristics of emissions, alpha, beta particles, and gamma ray. So I'm going to have first this. So we are going to look at the characteristics of emissions. So for easy understanding, I'm going to write here alpha. Then at the middle, I'm going to write beta particle. Then at the far end, I'm going to write gamma ray. So it will just be like a box. Alpha. So we are going to look at the characteristic of these emissions. So number one, we have nature. What is What is an alpha particle by nature? An alpha particle by nature, this is an helium and helium an helium nuclide. An helium nuclide, the symbol for an helium nuclide is 4,2He. Then by nature, what is a beta particle? By nature, what is a beta particle? A beta particle by nature, this is a fast moving electron, so we are just going to write electron. And the charge or the symbol for an electron, this is 0, -1. Then what is a gamma ray by nature? A gamma ray by nature is electromagnetic wave. Then we are going to move on to charge. So what is the charge of an alpha particle? The charge for an alpha particle is +2, while the charge of a beta particle is -1. Then a gamma ray has no charge, so we can either say it is neutral or 0. Then we are going to move on to mass. What is the mass of an alpha particle? So an alpha particle has mass of 4. When a beta particle, since it is an electron, we are going to get the mass for an electron, which is 1/18. Then a gamma ray has no mass, so we are going to write 0. Then we are going to move on to absorbed by the substances which can absorb these emissions, absorbed by. So an alpha particle is absorbed by simply a sheet of paper. A sheet of paper. A sheet of paper can be used to absorb an alpha particle, while a gamma ray is absorbed by 5 millimeters of aluminium. Then the gamma ray, this one can be absorbed by 5 centimeters of lead. Then we are going to move on to penetrating power. The penetrating power, So how is the penetrating power of an alpha particle? So the penetrating power of an alpha particle, it is very weak. Very weak. When the penetrating power of a beta particle is weak, then the penetrating power of a gamma ray is strong. So here all you have to know is comparison. So we are going to move on to ionization effect. How is the ionization effect of an alpha particle and a beta particle and the gamma ray? We are going to move on to the ionization effect. So we are going to write ionization effect. So here we had alpha, here beta, and here we had gamma, beta. And the symbol for an alpha particle, this is how it looks, and for a beta particle, this is the symbol for a beta particle. When the gamma ray is represented by something which looks like a 1. So how is the ionization effect of an alpha particle? So the ionization effect of an alpha particle is strong. Then of a beta particle, it is weak. Then the gamma ray, it is very weak. Then we are going to end by this characteristic, which is range in air. So what is the range in air of an alpha particle? A few centimeters, and the range in air of a beta particle is a few centimeters, a few meters. Then the range in air of the beta ray or of the gamma ray is hundreds of meters. So after talking about the characteristics of emissions, we are going to move on to something which is called radioactive decay. We are going to look at radioactive decay. So questions on characteristics of emissions comes in multiple choice questions. So it is a must to know all the characteristics. So we are going to look at radioactive decay. So before we dive into solving questions on radioactive decay, we first have to understand the meaning of radioactive decay, or what concerns radioactive decay brings. So radioactive decay, this is simply the changes that take place when an element emits alpha particles or a gamma ray. So on radioactive decay, we have alpha decay, beta decay, and gamma decay. The changes that take place in when an element emits these emissions. For example, when an element, I'll give an example of helium. Helium, when it emits an alpha particle, the changes which are going to take place on helium, of a product which are going to be produced this side, are going to be different when helium emits a beta particle or a gamma ray. So we are going to look at first, we are going to start by alpha decay. So what is alpha decay? Alpha decay, this is simply when an unstable element emits an alpha particle. So I'll give an example of this element, which is lithium. You will find it on the periodic table. Here we have 26 as the mass number. Then here 88 as the proton number. So when radium undergoes alpha decay, here we are going to indicate the symbol for alpha decay. So when radium undergoes alpha decay, the mass number reduces by 4, while the number of electrons will reduce by 2. So here we are going to write the answer. Since we don't know the element which is going to be formed here, we are just going to represent that element by x. So here we are going to have, since we have said the mass number is going to reduce by 4, here we are going to have 222, while the number of electron is going to reduce by 2. So we are going to have 86, then plus the helium nuclide. So this equation is a good example of an alpha decay. And this equation is balanced. Here the mass number we have 226. Here we have 222 plus 4. We are going to have 226. And on the number of electrons here we have 86. And here we have 2. When we add, we are going to have 88. So this equation is balanced, and the general equation for alpha decay, this is how the general equation for an alpha decay looks like. So here we have x, a representing the mass number, then z representing the number of electrons, and the symbol for alpha, then the element which is going to form this side, the product, it is going, the mass number is going to reduce by 4, while the number of electrons is going to reduce by 2. Then plus the helium nuclide. So this is the general equation for alpha decay. So this is the general equation. So now after talking about the alpha decay, we are going to move on to beta decay, so that we see the changes that take place when an element emits a beta particle. So we are going to write here beta decay. So in an element, we are going to give an example of using the same element, which is radium. Radium has a mass number of 226. Then the number of electrons is 88. So when radium emits a beta particle, the symbol for a beta particle looks like this. And the product which are going to form this side, the mass number remains the same. The mass number will remain the same, and the number of electrons is going to increase by 1. So 88 plus 1, we are going to have 89. Since we don't know the element which is going to form this side, we are going to write x, so that x represents the element which is going to form this side. Then we are going to say plus the symbol for a beta particle, which is an electron. Here we have 0, and here we have -1. So this equation is balanced. When you see the mass number here, it is 226, and here it is 226. So here 226 plus 0, it is 226. So the equation is balanced, and the number of electrons is the same, because here we have a -1. So 89 minus 1, we are going to have 86. Then the general equation for beta decay, this is how it looks like. So A, it is representing the mass number, while Z, the number of electrons. So here we are going to put the symbol for beta decay. So the mass number remains the same. So we are just going to write A since there is no change on the mass number. Then the number of electrons increases by 1. So we are going to write Z plus 1. Then conclude by writing the symbol for a beta particle, which has a mass number of 0 and a negative charge. So this is the general equation for beta decay. So we are going to conclude on gamma decay. We have this. So when talking about gamma decay, gamma decay. So we are going to use the same example of which we are using, which is radium. Here 226 and here 88. So gamma decay, how it is when an element emits a gamma ray, the mass number and the number of electrons remains the same. So this one is easy. So you are just going to write here X, or you are just going to write the same element, which is radium 88 plus the symbol for a gamma ray. So this is the symbol for a gamma ray. Then when we talk of the general equation for the gamma ray, this is how it is. The general equation, we are going to use X, then the mass number A, number of electrons Z. When an element emits a gamma ray, the mass number remains the same. So we are going to write A, then Z here, then the symbol for a gamma ray. Now after saying everything on radioactive decay, we are going to move on to the last part, which is half-life. So we are going to discuss what is half-life and how to solve questions on half-life. So we are going to look at half-life. So the definition of half-life is half-life. This is the time taken for an element to reduce by half of its original mass. So we are going to write the definition of half-life. This is the time taken for an or for a radioactive element to reduce by half of its original mass or material. So after knowing the definition of half-life, we are going to look at one example on how you can solve questions on half-life. So we are going to have this example, which was saying they are 1 kg of strontium. The symbol for strontium is SR. That has the half half-life of 30 years. Then question A is asking us to find how many grams of strontium. We're just going to use the symbol strontium remained after 90 years. So before solving this question, we are going to discuss the two methods of which you can use to solve this question. It depends on the situation, if it is on multiple choice or under section B or section C. So if you want, you can use the formula, which is the material multiplied by half, then period over time. So here, or if you don't want to use this equation, there are also some other ways which you can answer this question. But first, we have to know the meaning of these initials. So here we are going to say this means half-life, then M material or original material. Then the capital letter T means period, the total time taken. Then the small letter T means time taken. So when solving this question using this formula, this is how we are going to answer this question. So the question is saying they are 1 kg of strontium that has the half-life of 30 years. How many grams of strontium remained after 90 years? So here we have said how many grams. While in the questions we have 1 kg. So we are going to change 1 kg into grams. So 1 kg into grams, we are going to have 1000 grams. So this 1000 grams is the original material. Then the period, this is the total time. So the total time, this is 90 years. So this one is going to act as the original mass. Then 90 years is going to be period. Then 30 years, which is in the question, is going to be the time taken. So we are going to replace this on this formula. So M, we have said it is 1000 multiplied by half. Then total time taken was 90 over 8. So here we are going to have 1000 multiplied by 1 over 2 power 30 into 90, we are going to have 3. So 1 cubed is equal to 1, then 2 cubed is equals to 8. So here it is the same that we have, it is the same as having this. So the answer of which we are going to have here is 125 grams of strontium. So this is the mass of strontium which remains after the half-life of 90 years. So we are going to answer this question without using now the formula. So this is how you can solve this question without using the formula. So the original mass we have 1000, and this 1000 has not yet undergone radioactivity. So there is 0 years. Since time is given in years, so here there is 0 years. That is why we have 1000 grams of strontium. Then after undergoing radioactivity of 30 years as stated in the question, we are going to find that this original mass is going to reduce to 500 grams. Then after again undergoing a radioactivity or a radioactive decay of again 30 years. So we are going to add 30 years to this 30 years. We are going to have 60 years. Then here it will be 250 grams. Then again, these 250 grams again undergone a radioactive decay of 30 years. So we are going to add 30 years to this 60, and we are going to have 90 years. So we are going to find the mass of strontium to have or to be 125 grams. So this is how you can solve this question without using the formula. So after saying everything on radioactive half-life, we are going to have a word on nuclear emissions and nuclear fusion. We are just going to look at the examples of nuclear fusions and nuclear emissions. So here we are going to start by looking at nuclear fissions. Nuclear fissions. So the definition of nuclear fissions, this is the splitting process of every nuclide using a fast moving neutron to produce light nuclide and some amount of energy. So this is the splitting of heavy nuclei using a fast moving neutron. So an example of a nuclear fission. This is an example of a nuclear fission. Here we have an element with a mass number of 235, number of electrons 92, symbol is U. Then, as the definition is saying, using a fast moving neutron, so here we are going to have a neutron. A neutron has a mass number of 1, then 0 charge or 0 electron. That is why it is neutron. So this is the symbol of a neutron. So this element is going to be split using a fast moving neutron to produce the first element, which has 141 as the mass number and 56 as the number of electrons. Again, plus another element plus the neutron itself, and plus energy. So nuclear fission, this is the splitting of every nuclide using a fast moving neutron. So this is an heavy nuclide which has been split using a fast moving neutron to produce these lighter elements. Then we are going to conclude the topic by looking at nuclear fission. Nuclear fission. So nuclear fusion. This is the process by which the two light nuclides unite to form a heavy nuclide. So this is a process by which this is the process by which two light nuclei unite to form a heavy nuclei. So an example of a nuclear fusion, this is a good example of a nuclear fusion. Here we have the isotopes of hydrogen. They unite to produce a heavy nuclei. A heavy nuclei plus energy. So all the processes releases energy to the environment. So nuclear fusion, this is the combination of two light nuclei to produce a heavy nuclide. So this is all on radioactivity, and if this YouTube channel is helping you, you can comment in the comment section or come on Facebook. We talk about the things of which you need or some adjustments we need to make on this program. So if this is helping you, you can subscribe, share with your friends, and like, comment in the comment section. Thank you.